Welcome back, everyone. I'm Don Gillis with Emerson. I'm in Sydney, Ohio at the Copeland plant, and we are into day two or part two of modulation. Hopefully you got something out of the first part one of the modulation. Again, I'll have my email there. You can email me at don.gillis@emerson.com anytime you feel like it, and send me a message. Let me know how we did, if you got anything out of it, if you need any other questions. Let's go ahead and get started real quick on day two. All right, we're going to talk about digital now. Digital is a unique type of compression. The thing about digital is it's very precise. What I mean by that is it can keep the temperature within a half a degree. The humidity is very tight. Where some of the places you might see digital at is in schools, restaurants, and auditoriums. But look at the bottom here, the hospitals, the museums, and the supermarkets. The supermarkets are kind of our playground. Very, very good in a rack system, especially as the lead compressor. And I'm going to show you a little bit about that. Again, digital can keep the temperature within a half a degree. Digital originally was driven by the Asian market. And what I mean by that, overseas, ships, containers, and what have you with produce. If you think about bananas and how fast they ripen when you buy them partially green at the supermarket, set them on your kitchen counter, within a day or two, they're yellow. If you ever get a chance, look at the story of how a banana is even brought to the United States. It's pretty incredible. It goes right to cold storage in a warehouse and gets moved to our local shopping markets, supermarkets close by. It's a very, very fine process, and it entails a lot of tight humidity and temperatures. So let's take a look at some of the benefits of digital. This is just a digital scroll versus hot gas bypass efficiency comparison. Now, granted, hot gas bypass is not known for being extremely efficient, obviously, but let's just see, because it seems to be, way more common in refrigeration than digital is as of now. So let's look. We have our capacities over here on the left-hand side, 25%, 50%, 75%, 100%. We have the comparison of hot gas bypass EER and the digital scroll EER, and then our percentage of improvement. So let's take a look at 25% capacity. At 25% capacity, the EER for hot gas bypass is approximately 2.9, or let's just say 3. The digital scroll, on the other hand, is a 6.3. That's a 117% improvement in efficiency in the EER. So that's huge. That's a huge savings. And if you think about some of the bigger stores and multiply how many branches they have, what kind of savings that is, annually for all that. And as it goes up, it just keeps getting better until we get to the 75% mark. We're still higher than the hot gas bypass. We're still gaining, but not quite as much as when we first started out. And I'll show you this. Instead of kicking on all that horsepower from a larger compressor, we're ramping that up, if you will. It's not like variable, but I'll show you and explain to you what I mean by ramping that up. Significant part load efficiency improvement with the Copeland Scroll Digital. What types of systems can I upgrade to digital? Well, supermarket racks for sure, the food service industry, commercial AC systems, probably not residential for multiple reasons, but right now the biggest thing that I can think of is two things jump out at me. Money. It's not, there's an expense to a digital compressor. You wouldn't see that in a residential application. To be brutally honest, at least that's the way it was 5 years ago, variable speed was having a little bit of an issue taking off in the residential market because of some of the pricing out there. So just my 2 cents on that. The other thing about digital is they have a unique sound to them, so you have to be aware of that. And I know from installing a lot of air conditioners through the years at commercial properties and residential properties and what have you, we typically have those not all that far from a window sometimes. So the digital is going to make it's a different sound. So you have to be cautious about that. Walk-in coolers, freezers, refrigerant warehouses, process chillers, and air dryers, possibly. Overview, the digital upgrade benefits. So instead of shutting on and off on the digital, you're actually taking those scrolls and loading loading and unloading, loading and unloading. Okay, you have that 1 millimeter we talked about in the anatomy of the scroll. That's sliding up, so it's matching the load, and that's really what all this modulating is about. It's load matching, right? We're trying to load match exactly whatever that control is calling for, and not exceeding that to keep it as efficient as possible. Instead of slamming that whole RPMs on, or that whole BTUs or horsepower is coming out at the same time, will increase our contact life. You can see this visual here. See how that's all pitted up. Improves system load matching, as I mentioned. Improves suction set point range, and improves energy efficiency. Here's something we talk about a lot in our classes. In some suction set points are lowered to compensate for swings in suction pressure due to compressor cycling. By increasing the suction set point, and energy savings can be achieved. I think we all know that, but did you know for every 1 psi increase in suction pressure, compressor power is reduced by approximately 2%? Now, when they say power, we're not talking about the capacity. We're talking about the energy savings, okay? The electricity. We're reducing that electric bill by approximately 2%, okay? So that's huge. So remember that suction pressure, how important that is, keeping that suction pressure up. Can't emphasize that enough. So here's a digital compressor operation. On the left-hand side, we're showing it loaded. On the second picture on the right is unloaded. So in refrigeration, the way the digital works is it's in 20-second increments, okay? So in other words, this is showing that we're running for 4 seconds, we're loaded for 4 seconds. In other words, we're unloading for 16 seconds, loaded for 4 seconds, unloading for 16 seconds. By the way, never shutting off. Okay, we're just separating those scroll sets, that 1 millimeter that we talked about earlier. Okay, and by the inertia of that gas flowing through there, it doesn't affect it at all. It keeps moving. It's a quick, like I said, 16 seconds back on, but from the inertia that we're already pushing from the original gas flow, it keeps flowing. It's just like speeding down the highway. When you put your brakes on, you don't come to a complete stop. You still roll and coast. It's the same concept, okay? So at 20% capacity with 20-second increments, we're on for 4, we're unloaded for 16, loaded for 4, unloaded for 16, and so on and so forth. At 50%, same concept. 10 seconds loaded, 10 seconds unloaded, 10 seconds loaded, 10 seconds unloaded. So it's, okay, that 1 millimeter, just separating that scroll tips and stop pumping like that. All right. What type of applications or different models we have? We have the piston modulation and the loads by venting the top of the piston to a pole fix scroll up, and I'll show you that here in a little bit. In fact, I think I have something here. Let me see here. There's actually one right here. I don't know if you can see the threads on it or not, but the threads right here, almost like if you use black pipe or galvanized pipe, it has a plunger type deal here, and it will pull that fixed scroll up that 1 millimeter, okay? On the left-hand side, we have the smaller model. As I said before, it unloads by venting the top of the piston to a pull fixed scroll up. You can see all the solenoid and the copper tubing is on the outside of the scroll. This is not a handle, by the way. Please do not pick it up by that process, okay? This solenoid valve has been tested over 3 million times, so you can't just replace that with any old solenoid valve, and this will all be in your specs. But you can see what it's doing here, okay? It's bleeding off that gas at the top and allowing that fixed scroll to lift up that 1 millimeter. And over on the right-hand side, we have the larger from 9 tons on up, intermediate cavity modulations, unloads by venting intermediate cavity. So everything you see on the outside over here is on the inside here, with the exception of that solenoid valve on the outside. This is what I just showed you a little while ago. This is actually the fixed scroll over here that I was holding up. All right. And this is that floating seal that sits down inside that thick scroll. In fact, I have one identical here. It's got a little washer here to prevent any kind of expansion gas. It comes through the discharge line right there. There is like a check valve, if you will, but it's really like a flat washer. And you can see the holes here on the bottom. That washer, when it comes down, it blocks those. If the gas should try to come back in from the discharge pressure at the top of the scroll, it stops it. All right. And here's some of that tubing internally I talked about on the larger digital that we're seeing in that copper tubing on the outside. Okay. Piston modulation, you can barely see it, but there's three little holes on this plunger right here, okay? And this is our floating seal. This is the fixed scroll bolted down with our Oldham coupling on top of our orbiting scroll, okay? And the way that is, it's a plunger. Again, it has male threads on the end of it. And when that scroll lifts up, and basically the way this works is this is trickling out gas all along the way, and the major part of the gas, this is above that muffler plate that we talked about earlier that separates the high pressure from low pressure, and this is coming out of our plunger above that muffler plate. All right, and it's running right now. These three holes here are bleeding off just enough gas to push off the top of the compressor and push it down. All right. And I'll show you what happens. Now they've added the muffler plate over here, and you can see the holes inside that plunger, that piston, if you will, that's blowing the gas out, coming through that discharge line in the dead center of that scroll set. Now, what happens here is you can see this, and for capacity, you can see we've got little lightning bolts coming out there to indicate that we have power to it. This is normally closed. All right, now it's running it's running full capacity. It's loaded right now. Notice that when we hit the electric here, okay, now it's charged, it's opened up, and it's bleeding off that gas. Remember those three holes I told you at the top of those plungers that's normally bleeding off a little bit of gas, causing that to push back on the fixed scroll? Well, when this gets opened up, that little bit of gas that's bleeding out through that plunger on the digital, it has nothing to stop it there. So it then bleeds off and into the suction gas, back into the suction gas, okay, mixing with this incoming gas there. So that's the way it works. Let's watch this solenoid valve again. There we've got electricity coming to the ceiling valve. It's calling, and now we're bleeding that off. So we're unloaded. Now we're loaded. Again, with the exception of air conditioning, the refrigeration is going to be in 20-second cycles. All right, 20-second increments. On air conditioning, that's going to change to 15 seconds. So it's going to unload or load for 4 times a minute. Now, if you were to detect some type of problem here, there's a lot of different ways you can attack this. You can pinch off this tube if you like. If this fails, it's going to be like a fixed compressor, basically. And this is just a larger picture of a digital scroll modulation and how it works. You can see the same concept. The speed of it's slightly exaggerated here. Again, the scrolls run 3,500 RPMs. If you didn't know that, they're 2-pole motors. All right, so they're running twice as fast as the 4-pole motors, which would be like 1,750 RPMs at 60 hertz. So Copeland Scroll Digital, let's take a look at this in some applications. So here's a nice application. Let's pretend this is in some type of a rack system. Let's say it's a supermarket and it's a holiday weekend and you're getting all your goods and what have you before the holidays. Down at the bottom, you can see the compressor. This is our digital, the lead compressor. The rest of these are all fixed compressors. Notice this is a ZBD 45 digital. These are 38 fixed at the way, okay? So 159,000 BTUs, medium temp system. Here we go at the store, and the day starts to pick up, and we call for the first compressor to come on. Again, this is somewhere between 10 to 100% of its capacity. It won't come on until it calls for at least 10% of its capacity. So at ZBD 45, 10% is going to be 4.5, 100% is going to be 45, okay? So we're calling for it at 10% on startup, the digital. So 10%, it's on, off. Now we go up to 52%. See the graph up here, all right? So now we're running at 10 seconds on, 10 seconds off. And when I say on and off, excuse me, I'm used to saying on and off, but it's loaded or unloaded. It's not shutting off. The digital is not shutting off. That's the sweet part of having a digital, okay? You're not turning that on and off and running that electric bill up, all right? Those contactors aren't getting pitted. So let's take a look at this. As more people come in the store, we get around 1 o'clock, and the peak the season, it's getting hot outside. All the cooler doors are getting opened up. This is medium temp application, it's stating. All right, everybody, now we're starting to fill the store up with more people. We call for this. Now we're calling for this, for example, let me back up a little bit here. When we're calling for this, when we get to the top of this 45,000 up here on the digital scroll, what's going to happen is by communication, it's going to tell the second compressor that, hey, I can't hold this anymore. I need help, as racks do, and it's going to come on. But the great thing about this is if we're already peaked out at 45, it's going to ask for help. The 38 is going to come on. Notice down here, the 38 is on now. This is going to ramp down, all right? It's going to load match. So in other words, instead of being 45 as it was, now that we have this fixed compressor at 38, this is going to ramp down to like a 7 BTUs, okay? So that's what it's going to do. It's going to match the load. And as it calls and keeps going up and the store starts to fill, it's going to max out. We're going to get up to that 45 and that 38, okay, which would be what, 83, I believe? Okay, once it hits that peak, it's going to ask for help from the third fixed compressor. So in other words, instead of kicking this 38, if this was a 38 fixed compressor, as opposed to a digital 45, and kicking that 38 when we might only need 4.5 and start it up gradually, sort of like a variable does, we're saving a lot of energy. We're load matching, okay? And this goes on and on and on. Each time, every time a compressor is called on, the digital compressor ramps down to match the load needed. At 100%, we're 118 or 159,000, okay, BTUs down here at the bottom. Now, as the store starts to empty out and the sun starts to come down and we start to cool off the store, the same thing happens. It's going to start coming down. You can see, again, load matching. Keeps going back to the load matching. Every time it drops off a digital or a fixed compressor, pardon me, it load matches that digital. The digital loads down, then ramps up as it's needed until it's completely shut off. Again, back to zero, all the compressors are off. So that's how digital works in a rack system. It load matches that, okay? It matches the load, the next fixed compressor that comes on. So if you get in an opportunity where a compressor goes down on a rack, this would be a great opportunity to help a customer out to add that digital compressor. Controllers. On the left-hand side, we have 2 of them, and I'll show you what that looks like. Open loop means that there's some type of third-party controller of some sort out there, whether it be a thermostat or someone else's controller out there with a set point. This is the IDCM, and I'll talk about that a little bit more. This, again, requires an additional system controller, and then we have the EC3, DC72 or D72, and I'll talk a little bit more about that. And then we have this standalone controller on the right-hand side, and they refer to that as a closed loop. Now, for you geothermal people, I know we think closed loop is a closed loop. It's not an open loop. It's not a pump and dump in geothermal. But what they're saying here is it doesn't need a controller. All it needs is this standalone controller, and that's what we're referring to as a closed loop. Now, on the IDCM board, some of the protection features, a digital control, obviously, locked rotor, high discharge temperature trip, compressor trip, demand signal, discharge thermistor fault, and then a welded contactor. So if that welded contactor, gets welded on one of the phases, instead of it burning up the compressor, what it does is it calls for it to come back on. That's how the protection is developed on the welded contactor. All right, so it comes back on, it sets off an alarm, whether that by a strobe, a sound, going to your E2 or whatever the controller is. Okay, we're running these wires through here. If it's three-phase, you've got T3, T1, and T2. If it's single phase, we've got R, common, and start, runs common and start, pardon me. On this side over here, we have our low voltage. On this side over here would be our high voltage coming out. And it bolts in with this screw right here. You'd actually only see this end down here, and you can't really see it, but there's LED lights at the very end, which you would put this in either at the system or on the rack or in a panel of somewhere. Down here is just some part numbers. Again, all the cycles are 20-second cycles, with the exception of the 15-second cycle that's for air conditioning scrolls. I'm not going to go through this whole wiring. I'll just pick out some things here. Again, low voltage on the left-hand side, high voltage on the right-hand side. We need to route T1 through the current torque here, okay, because this is picking up the amps as it's coming through. As I talked about earlier, it's reading those. If you're using a pre-existing discharge line temperature probe, use the resistor to jump across T1 and T2. Some of the other things here, for the 6D compressors, use V1 and V2 for a blocked suction, okay? And the V1-2, this is for vapor injection solenoid. And I'm not going to really get into vapor or liquid injection, but that'll be for another day. So how that works with the open loop Copeland digital scroll controller, we have the OEM system controller. We started off at the set point, comes back through the IDCM. The contactor pulls in. We send out the IDCM. I'm in trouble saying that today. It sends out the capacity signal to the scroll compressor, to the digital, okay? So if it's calling for 50% in refrigeration, we've got that coming in, and it's telling it 10 seconds on, or 10 seconds loaded, 10 seconds unloaded, and so on and so forth. We're coming out of the contactor, the compressor start, stop, back to the IDCM. If we get an alarm, it comes back to our controller. The capacity solenoid control modulates solenoid based on capacity demand. A minor alert will display appropriate alarm. A major alert de-energizes the contactor to lock out the compressor. Okay, 10% is the equivalent of 1.4 volts. So at 100%, we're 5 volts, okay? You can see the unloader modulation percentage-wise over here. So at 10%, again, it's equivalent of 1.4 signal volts on the demand on DC. At 50% would be 3 volts DC. Input signal, digital controller receives 1.4 through 5 volts input signal from the system controller, and it corresponds to 10% to 100% compressor capacity. Digital controller options and applications, single evaporator application. You can see the system controller over here. We have that EC3-D72 board, EXV, our compressor. Could be a discus or a scroll digital AC refrigerant over here, and all these different applications. All right, this controller, we're gonna ask you to use this controller when you're using an EV. If you're using for a single evaporator application, use with either a single digital compressor or digital and standard compressor connected in parallel. Can be used with digital discus or digital scrolls, and it provides synchronization between the EXV and the digital compressor to prevent refrigerant from overfeeding or underfeeding when the digital compressor unloads. That's the huge part of it. Highly recommend this. In fact, it's a must. Strongly recommend for DX evaporators. The only controller that works with the braze plate evaporators due to limited charge and circuiting. Open loop controller requires an additional system controller. For example, Johnson Controls C450 series or the Honeywell T775 series to operate. The maximum system capacity of this type of system is 30 tons at HT operating conditions for the EX6. All right, so let's see how this all works together. We've got the valve controller for the digital application, the EC3-72. I'll try not to butcher this for you. So our controller's dead center here, coming back from the EC3-DXX, in other words, is back to the system controller. Remember, this is an open loop. We've got compressor 1 and compressor 2 run signals, okay? Synchronization of the valve and compressor can control single or tandem compressors. And the superheat is measured by the pressure transducers and the temperature sensors you see, okay, measuring pressure and temperature. A third-party controller, as we talked about, is required and to measure the box or the case. 0-volt signal would be minimum compressor capacity, and the 10-volt signal would be maximum compressor capacity. All right. So we have 2 compressors, and we are coming back here to our metering device, into our evaporator, back to our compressors, out of our compressors and our condensers. Okay, and back to it. So we got our box temperature here. All right, and we're coming through the EEV. Remember, we need the electronics to go back to the DXX. It's measuring the pressures there, opening and closing as needed. Let's take another look at this. So if the capacity is less than 70%, the EX valve freezes at the current opening percentage during the no pumping. Let me repeat that again. If it's 70% or less, all right, the EXV valve freezes, or EX valve freezes at the current opening percentage during the no pumping. If it is greater than 70% or greater, the EX valve closes to 0% during the no pumping stage. The expectations: when the second compressor is active, the superheat control loop is continually running. Now, this is just that smaller controller. This is what we referred to earlier as the closed loop. All right, Emerson closed loop digital controller, the XC643. The protection and features: it controls a small rack or condensing unit applications, normally no more than 2 compressors or 2 fans. Simple standalone controller, programmable perimeters to support custom settings, and multiple refrigerant setup capability. So that's pretty cool. Got a hotkey here, which basically means that it's like a thumb drive. You're pushing it in there. A lot of times, if they have multiple coolers or freezers or whatever, they'll take their hotkey and they'll program one, and then they'll take the hotkey out and just move it on down the line and program the rest of them the way it is. That's done very common with the super heat controllers and what have you out there, okay? There is an AE bulletin on this, AE-1386. Again, going back to those applications, those apps we have, AE app and the Copeland Mobile. Don't forget those. By the way, you can get to the AE bulletin app through the Copeland Mobile. Plenty of resources out there, multiple AE bulletins here to look into for the digital controllers and what have you. There's also a Copeland Scroll digital retrofit kit. The upgrade kit features the new Emerson commercial comfort controller and the required valve, coil, thermistor, and tubing needed for a complete compressor replacement. Features networkable thermostat and controller, external valve with 24-volt coil, and the discharge line thermistor, which is huge, and then some copper tubing. You've got your kit part numbers here and the description on where the horsepower falls, all right? See if we can get this to play for you.
The following video outlines the steps necessary to install a Copeland Scroll digital compressor using the Copeland Scroll digital retrofit kit featuring the Emerson commercial comfort controller. Before beginning any new installation or retrofit of an existing compressor, be sure to consider all system and component implications such as compressor clearance, expansion device, airflow, and controller wiring. Ensure that all proper safety equipment is used and procedures are followed, and that all relevant product manuals have been read and understood. To begin the installation process, the existing compressor must first be removed. Be sure to disconnect and lock out all power to the system. Remove the unit's service panels and connect gauges and recovery equipment to properly evacuate the existing system refrigerant. Once evacuation is complete, disconnect all electrical connections near the compressor, like the molded plug and pressure switches. Cut the copper connections and free the suction and discharge lines from the compressor. Undo the mounting bolts and the compressor can now be removed. Begin the installation of the new compressor by first setting it in place and inserting the mounting bolts. Fit the new copper tubing and valve in place and adjust the lengths as needed. After ensuring proper fit, braze in the new copper tubing. Make sure the new valve is protected from the heat of brazing. A wet rag is commonly used. Next, install a new filter dryer to remove any contaminant introduced while the system was open. Once the system is sealed again, begin leak test procedures by adding nitrogen, monitoring gauges, and identifying and fixing leaks as needed. Next, begin the evacuation procedure to prepare the system for new refrigerant. While waiting, reconnect all electrical points and switches. Install the 24-volt coil to the newly installed valve. An additional 24-volt wire is required. Install the discharge line temperature sensor, which snaps in place, and properly insulate it. Lastly, add the appropriate amount of refrigerant as specified by the manufacturer. You can now begin the installation of the Emerson Commercial Comfort Controller. The first step is to pull the appropriate wire from the rooftop unit back to the thermostat in the conditioned space. Once the wire is in place, mount the back plate. While wiring the comfort controller, be sure to record the chosen wire connections and colors. After snapping on the controller cover, it is time to head back up to the roof. Inside the unit, make the electrical connections, remembering to tie in the additional wires from the 24-volt coil. Once all connections have been made, power on the unit and program the Emerson Commercial Comfort Controller. You may need to change the settings based on the application, either rooftop or heat pump, and you may also configure the set points or program a defined schedule. The last step in the installation process is to check for proper operation of the compressor and controller. Ensure the digital compressor is modulating as expected and the controller is sending the appropriate signals to the rooftop unit. Now, reinstall the condensing unit panels and enjoy the added benefits of precise temperature and humidity control offered by the Copeland Scroll digital compressor and the Emerson Commercial Comfort Controller.
We installed the digital scroll compressor with the new controller at a local school yesterday, and all the pieces that we received in the kit worked perfectly. We didn't have to fabricate anything. The unit started up, it ran just like it's supposed to. That compressor can be installed when you're in a replacement mode. When we have a dead compressor, using that kit, it doesn't take any more time to install that as it would to be installing a replacement compressor. The benefit for the customer is that he would have a modulating compressor. The unit would then match the load inside his building. And he would get a new thermostat that's programmable.
For more information, please visit our website at emersonclimate.com/digital retrofit kit.
I love that video immensely. It's not too salesy, and I really like it. We don't try to get too salesy in our technical classes. So, all right, everybody. Now we're going to talk about variable speed and try to take some of the mystery out of this. If for some reason I don't get all your questions answered, feel free to email me. I have it on the last slide here at our goodbyes. So let me see if I can clear this up a little bit for you. Variable speed, seeing a lot of it now in all phases, everything you can think of. The residential folks I know are seeing it, the light commercial and what have you. Really, really good application for humidity and comfort issue, okay? So what do we need for variable speed? We need a compressor, we need a drive, we need some type of controller. The system controller provides speed signals to the motor drive. The motor drive then converts the AC to DC, okay? And then back to AC. And that sounds confusing, but I'm going to show you how that works here in a little bit. And it sends to the compressor the brushless permanent magnet motor, dynamically adjusting the speed. The drive then manages the compressor operation to ensure efficiency and protection from adverse circumstances. The drive also communicates diagnostics back to the system and controls and loops it, continually repeating it over and over and over. If you think about it for just a second, a fixed speed compressor, the compressor is either on or off, right? And who has heard that old saying, the objects in motion tend to stay in motion? Objects at rest tend to stay at rest. Similar to that applies here. When we start a compressor from a stopped position, it takes a lot more energy than if we continually run it, going back to our digital segment, okay? So one advantage of the variable speed compressor is that energy consumption is less overall. And we'll discuss the other benefits in the upcoming slides. And hopefully I didn't confuse you too much on that. All right, how does it work? Again, we can either have three-phase or single-phase coming in on the line. But at the end of the day, at least with our drives and our variable speeds, we're going to be throwing three-phase out at the end. So we're going to convert it to the AC to DC, and then we're going to invert it back to the motor as three-phase. So whether it's single-phase or three-phase coming in, the motor will see three-phase on our compressors, all right? That's how it works. So AC-DC, we're converting this first section. This is the board, okay? So visualize a board. This is full of diodes, and it rectifies the AC to DC. It then cleans it up and converts it to DC, as we said, and then we have a DC bus, which I want you to think about that as a normal capacitor in the center there. And it helps stabilize that inrush current, cleans it up, and it's just a storage area, really. So it helps convert that inrush current coming in, all right, stabilize it. And I'll show you another graph here in a little bit. And then we go back to DC pulse width modulation, or PWM, and then we change it. And the way we do that is, you know how alternating current works? It alternates. DC is direct current, keeps going. So we're using this DC, and we're using switches, if you will, to make it look like that it's seeing AC. And I'll explain that here in a little bit too. All right, now here it is one more time. Today's VFDs are pulse width modulation style drives. Frequency equals sine waves per second. So here's our sine wave, okay, positive, negative. There's our normal sine wave. Again, we're taking in either single phase or three phase into AC, alternating current, changing it back to DC, all right, through our diodes, rectifying it, sending it to our DC bus. We're cleaning that up. Now look at this. Look how unerratic that is right now, and how erratic it is over here. We clean that up. It's more stable. And it also, like I said, these are capacitors, if you will. It's storing that, so it helps with that inrush current. And then our DC, we're going to go back to pulse width modulation. Now, this pulse width modulation, this might look a little confusing, but really, this is really all it's telling you is how long those switches, or there's insulated gate, or IGBTs, insulated gate bipolar transistors, are open and closed. So by opening and closing those, we're changing that current, and the DC looks like AC. We're really manipulating the hertz of the motor is what we're doing, okay? We're manipulating the frequency, and we're slowing that motor down or rising it up at a gradual speed. And that's how variable speed works. So not that you need to know this when you're out in the field, but when you're teaching it, you want to just know the longer these lines are here, that's the longer it's staying on, okay? If they're shorter in sequence, they're coming on and off, and that sine wave will be tighter, okay? It won't be near as high and low as this is. So the more often you're making those switches, we're getting less hertz. That line's going to be closer to the center line, if you will. Here is what is an AC variable speed drive VSD. Here's what we're talking about. We're rectifying it where you've got the fixed DC voltage here, and then we've got these inverters. These are switches. We've got 6 of them here. These insulated gate, or IGB transistors. We're opening and closing these. So if we had DC, real DC voltage, we would be going in one direction, direct current, right? Well, what we're doing here is we're clicking these switches on and off and making it look like alternating current. And there's different avenues this can take to this motor to work, okay? For today, all we need to know is think of them as switches, all right? They're inverters, transistors, again, and it's changing it over and over again, that frequency. We're just manipulating that frequency. So we're using the DC and tricking the motor to think it's AC. And here's one more slide, as if you didn't have enough of it already. Let me move my picture down here a little bit. Newer VSDs have a variety of parameters that can be controlled by numbers programmed into it or downloaded from another microprocessor controlled system, such as a programmable controller. Now, all VSDs operate on this three-stage approach. Again, diodes, AC to DC, converted over, aka three-phase power rectified. Then we've got the DC bus. Again, think of this as a capacitor if you're not familiar with it, okay? Simplified representation of DC intermediate circuit includes the filter. So again, we're filtering that, keeping it stable, all right? Cleaning it up, if you will. And that helps prevent on that inrush current coming in from the diodes. And then we've got the IGBT, which is nothing more than insulated gate bipolar transistors. And we're manipulating those switches again to make it look like it's AC. It's an AC motor, three-phase variable frequency output. And you can see here the voltage pulse, the desired waveform. Again, the faster we're making those switches go on and off, the smaller that wave's going to be here on this. One last time with a little bit of animation. Stage 1, rectification, converts AC to DC. Stage 2, DC bus. It cleans it and it boosts it from 350 or 650 VDC, okay? Stage 3 is the inverter. It creates a false AC power, high-speed switching of DC power at different levels, tricks compressor to see AC power. And that's what it's doing, okay? The gates. Every VSD operates based on this three-stage premises. See if we watch this video, if it helps out a little bit.
For residential heating and cooling, Copeland Scroll variable speed technology enables HVAC equipment to precisely match system capacity with the home's heating and cooling demand to deliver a whole new level of efficiency, comfort, and reliability. So how does it work? Traditional HVAC systems are either on or off based upon a home's heating and cooling needs. A variable speed system runs at a wide range of speeds to precisely control the heated and cooled air throughout a home. It keeps households more comfortable by continually monitoring system operation to maintain the set temperature on the thermostat. Within air conditioners and heat pumps, the unit's system controller and variable frequency motor control drive dynamically controls compressor operation based upon demand. First, the system controller sends speed signals to the variable frequency motor control drive. Then the drive dynamically adjusts the brushless permanent magnet motor operation. The compressor speed is managed to ensure optimal efficiency and protection from any adverse conditions. And finally, the drive algorithms provide feedback to the system controller to optimize operation. At the component level, technology updates enhance and optimize the proven Copeland Scroll platform for added efficiency and reliability. These features include intermediate discharge valves to boost efficiency across a range of conditions, optimized scroll elements for improved performance, brushless permanent magnet motor technology for maximum efficiency, and a positive displacement oil pump to ensure reliability. Emerson's variable speed motor control drive features include integrated core sense technology for compressor diagnostics, protection, and communication, LED status display for simplified diagnostics, and an updated service tray for easier contractor accessibility. So, what are the benefits? By balancing the home's heating or cooling based upon the demand, variable speed systems deliver breakthrough efficiency, providing superior heating and cooling operation to enable systems to achieve 25 plus seasonal energy efficiency ratio and 13 plus heating seasonal performance factor, while also improving homeowner energy savings with up to a 40% reduction in annual energy costs. Revolutionary comfort, with more consistent temperature control compared to other technologies. And better humidity control using a broad range of compressor speeds from 900 RPM up to 7200 RPM to maintain a continual airflow. Proven reliability. Over 25 years of scroll development and expertise were leveraged to develop a proven and reliable compressor. When paired with an Emerson variable speed drive with integrated core sense technology, you augment this reliability and optimize operation. So, for your next residential heating or cooling project, Copeland Scroll variable speed technology makes the perfect match for more comfortable and energy-efficient homes. To learn more about Copeland Scroll variable speed compressor technology, please visit us online at www.emersonclimate.com/modulation.
Very nice little video there. Hopefully you got something out of that. I'm not going to beat these up too much longer. I think I've hit it pretty good. I think the video did a really good job. The green is showing you the variable speed compressor. The blue is just showing you the standard air conditioning or heat pump. Okay, and you can see how erratic that is and how constant that temperature control is right there with the variable speed. Maintains precise temperature control for enhanced comfort. Here we just have our chart. We have the temperature on the left-hand side. We have the humidity at the bottom, our envelope showing it's too warm at the top, too humid, too cold, and too dry. Broad turn down range enables more consistent humidity control. Very, very good humidity. And I think most of you know that, the people that I talk to online and some of the chat groups and what have you, very, very intelligent trainers out there. I've met a lot of them. So hotter supply air, the gas furnace up here, it says gas furnace air too hot. Anything fossil fuel is going to be hotter, obviously. May need humidification. Don't send any mail into me. I'm just the messenger here. Variable speed, it's a warmer air supply. May or may not need a humidifier. Again, I don't want to get into that. Compressor design enables heat pumps to supply hotter air during colder winter. Seeing more and more heat pumps in where I'm at right now. Years ago, when I put mine in, I have natural gas and a heat pump. So my first stage is my heat pump. My second stage is my natural gas. I did it all myself. I ran my own gas line from the main, actually up to my house and everything. I didn't have natural gas when I first moved into my house. I had fuel oil. So I converted it all over, put all the ductwork in. Anyways, now it's kind of neck and neck because gas prices are down really, really low. But in normal years, when fossil fuel was higher, that heat pump. But now getting back to, I kind of got off topic there, getting back, I see more and more heat pumps around all the time and a lot of mini splits out there. Variable speed compressors, not going to hit this nomenclature too much. You all know how to read nomenclatures. The Z obviously is our scroll compressor. You can look at this on your own, but it just goes through and tells you what these mean. The V is a modulation. Some of the platforms applied to, obviously we have the drive. We can add to residential, geothermal, rooftop units, or chillers. On the commercial side, variable speed system types, products, fixed speed compressor plus a drive. Operating range on that is 35 to 75 hertz. Remember, we're really manipulating that hertz and converting that, and that's what's causing that speed to go up and down. We stayed out of this variable speed market for a long time for fear of lubrication. All of our scrolls, with the exception of the variable speed, all run 3,500 RPMs. We like that because we lubricate by that shaft coming up in the scroll. This actually has a pump built into it at the bottom. So if that's ever a trick question on a test somewhere, you'll know that. Variable speed compressors with BPM, brushless permanent magnet motor, plus a drive will range from a 15 to 120 hertz. Emerson uses a true variable speed BPM motor plus drive. So again, how this works is we have our controller. Okay, system controls provide speed signal for the motor controller, which sends it on to the compressor. Drive converts AC to DC power, sends it to the compressor. The brushless permanent magnet motor dynamically adjusting its speed back to the drive and sending it back to the controller once again. Drive communicates diagnostic to system control. How variable speed technology works, I'm not going to beat this up. We kind of went through that already. I stuck some slides in there on a presentation I have where I'm teaching inverter technology. So I use those at the beginning. Not going to beat that up real whole bunch there. Ranges are from 20 to 120% modulation. The HV valve on the unitary compressors of 41 cc and below. So the HV valve is nothing more than a check valve. It reduces the volumetric efficiency. So that's what it does. It's a check valve so we don't get discharge gas back into the scroll set, causing that volumetric efficiency. Unitary products range from 900 to 7,200 RPMs. And commercial products range from 1,000 to 7,200 RPMs. This is just showing our envelope. Once again, the RPM range is determined by where inside the envelope the compressor is operating. The oil boost cycles are built into system and varies by manufacturer. After the system operates at low speeds for a defined period of time, typically 2 hours, the system will ramp up to a higher RPM for a couple minutes and have the oil boost cycles. Variable speed drives nomenclature. Again, we're going to have two different nomenclatures, one for the drive, one for the compressor. All right. Unitary drive cooling options. We have an air cool. We also have a refrigerant cooled. It's mounted on the refrigerant, inverter drive, OEM accessory, and a cooling plate back here. Again, more some of the nomenclatures, the family series. I'll go through these fairly quick. I know I'm running late. Bill of materials, production, variation, configurations, letter, number. Number 1 is the cooling fans, and this is the image. Number 2 is the flat plate. Again, your image. And number 4 is the fan cooled style. So know what you're getting. Just a bunch of AE bulletins on residential platform application engineer bulletins. Again, refer back to our apps that I talked about at the very beginning. And then we have the commercial platform application bulletins and drive user manuals. Soft starting. The drive will start the compressor and ramp its speed up to 1800 RPMs in approximately 2 seconds. The drive will maintain that 1800 RPM command for approximately 10 seconds. After 10 seconds, then ramp the speed to the speed requested by the system controller at a rate of 200 RPMs per second. If the compressor fails to start, the drive will initiate a restart command. So let's go through these one by one. Startup and shutdown. The compressor fails to start. If the compressor fails to start after 5 successive start attempts, the drive will shut down the compressor and indicate a high current fault to the system controller. Controlled shutdown. When the system is controlled, signals for the compressor to stop or request 0 speed. The drive will ramp down to 800 RPMs at the rate of 200 RPMs again per second. At the 1800 RPM, the drive will shut down the compressor. If we should have a minor fault during operation, if a minor fault condition occurs during the operation, such as a motor temperature fault, the drive will perform a controlled shutdown. Hard shutdown is defined as follows. If a major fault condition or lost power occurs during the operation, the drive will perform a hard shutdown. Immediately disconnects power to the compressor regardless of the compressor running speed. A hard shutdown is done by minimizing the damage to the drive and compressor or the system. Drives with integrated CoreSense technology. Of course, you can put CoreSense on there. The benefits, the compressor is controlled, the compressor protection, the monitor diagnostic, protects compressor and system from running outside the designed perimeters. In summary, 2-stage compressors use mechanical unloading to operate at 67% and 100%. First stage being 67% and 100%. Multiples allow modulation of compression capacity while maintaining efficiency and potential reduction in cost. Scroll Digital offers compressor modulation from 10 to 100%, allowing for precise capacity temperatures and humidity. Remember that temperature within a half a degree. And last but not least, in our variable speed HVAC systems, the unit system controller and Emerson's variable frequency motor control drive dynamically control the compressor operation based on demand. I want to thank everybody for coming out. I want to thank for the ESCO group, HVAC educators, for allowing us to attend. Emerson is grateful, and hopefully I'm still trying to reinvent myself with this virtual type teaching. It's still somewhat uncomfortable for me. I'm much better when I'm delivering it live, probably like we all are. But anyways, my name is Don Gillis. I'm obviously with Emerson. I am the lead technical trainer, as I said at the very beginning, in educational services. And there is my email, don.gillis@emerson.com. If I can be of any help ever, feel free to hit me with an email. And I appreciate all you tuning in. I wish you all the best for 2021. And hopefully I'll see you all soon. Be safe out there. Thanks a lot. Bye. All right, everyone. I hope you got something out of it. Again, my email is don.gillis@emerson.com. If you have any questions, feel free to reach out to me. Again, I am Don Gillis with Emerson in Sydney, Ohio at the Copeland plant. I wish you all the best and get the most out of this training you can. I only ask that whatever you learn from all the instructors, please pass it on. Share the knowledge. And if you're still running service out in the field, as always, be safe out there. Lockout, tag out. Y'all take care now. Thanks a lot. Bye.